all the way from the naturally occurring, the bromocriptine, the pergolides, and so on, and then we go to the others, the ergoline, the other ergoline derivatives, we go to apomorphine, and finally the rotigotine. So those are the dopamine agonists. Dopamine agonists, which definitely will act like dopamine. Then also we have the other class of drugs, which we are calling the metabolic protective agents. Metabolic protective agents, some of them we have mentioned them. These are the drugs that you give to prevent the dopamine from undergoing metabolism. So all you need to understand, what are the different types of metabolisms we have for dopamine? The different metabolisms is whereby, of course, to protect dopamine, the different metabolisms is where you can have catechol methyltransferase. You can also have the monoamine oxidases, and of course, if you give L-DOPA, then you can also have dopa decarboxylase. So the first protective mechanism is what we've already discussed, where you have the L-aromatic amino acid carboxylase inhibitors, and in this group, I didn't mention them again because we have discussed them at length. That is where we have carbidopa. And what we are saying is that you can give, one of the areas where you can have metabolic protective agents is where you give replacement agents like L-DOPA. And then together with L-DOPA, you give a metabolic protective agent, which is carbidopa, to prevent, as we have said, the L-DOPA from being metabolized in the periphery, to allow it to raise high concentrations. Of course, you remember, with high concentrations, it will be to move better through the membranes, the lipid membranes, and raise and have high concentrations in the brain. So that is one metabolic protective agent, which we have already discussed. The other metabolic protective agent is monoamine oxidase inhibitors. We did realize that, of course, in the periphery, it can be metabolized by the monoamine oxidase A. But within the brain, where we require it, we do have a selective monoamine oxidase, which is monoamine oxidase B. So we can look for drugs that are specific for monoamine oxidase B and not for monoamine oxidase A. Why would we? Because I've not even asked any questions. Why is it important? Why is it important that we get selective monoamine oxidase B inhibitors? I can see we are 30, the others now. The problem with students, most probably all these other ones are doing their projects. You get late in one area, you lose in another area. So why is it important that we give monoamine oxidase, selective monoamine oxidase B inhibitors and not non-selective? Why is it important for us to go for selective monoamine oxidase B inhibitors? Can I get an answer? Why is it important for us to go for selective monoamine oxidase B inhibitors? There's a more selective drug, that's correct, or it will reduce toxicity. But why? Why would it reduce toxicity? That is correct. But how would it reduce the toxicity? Minimize toxicity and systemic side effects. Which side effects will it have? It means minimize toxicity and systemic side effects means I require specific answers. Christine, non-selective will also target monoamine oxidase A, which is present in the periphery. And what will happen? Non-selective monoamine oxidase inhibitors may result in adverse effects such as cardiovascular stimulation as a result of inhibition of the ACE. That is why that is good. Eleka, very, very good. That's good. I think for the non-selective monoamine oxidase inhibitors, it will inhibit the degradation of other neurotransmitters centrally, such as serotonin and noradrenaline, which are sympathomimetic. Non-selective may cause thiamine pressure response. Correct? That's correct. Very correct. So you are there, but now you're in 50. I need very very specific answers. Let us not beat about the bush, because you have to answer the answer must be, let's call it, precise and concise. It must tell us that it must show me that you know what you're talking about. You're not beating about the bush. And somebody has mentioned it. You see, we have the monoamine oxidase in the periphery. We have monoamine oxidase B in the brain. If so, the monoamine oxidase in the periphery, what is its role? Is of course, even it actually will bring about degradation of any catecholamines or any derivatives. And somebody has said to me, if you give monoamine oxidase A, also inhibit the monoamine oxidase A in the periphery. Now, even in your foods, if you take even foods that have compounds that have agonist activity at the amine receptors, at the catechol or at the neurotransmitter receptors, then you will get what we call the hypertensive crisis. This is so you do require to be very selective so that you target the monoamine oxidase B metabolizing the dopamine. So you go for monoamine oxidase B in the brain, which is responsible for metabolizing the dopamine, and you leave the monoamine oxidase A within the periphery intact to continue the metabolism of not only the catecholamines, but also any other compounds that you may take, including foods like cheese, which have theramine, so that you may protect this patient from what we call the hypertensive crisis. So yes, therefore saying selectivity here is very important for us to target the monoamine oxidase B, which metabolizes the dopamine, and allow or leave the monoamine oxidase A within the other catecholamines and even amines found in food, so that we can, as I have said, protect, prevent what we are calling the hypertensive crisis. So your answers are kind of there. So we are saying we have monoamine oxidase B conservation of presynaptic dopamine by retardation of its catabolism by monoamine oxidase is therapeutic in managing the symptoms of FPD. Early use of non-selective monoamine oxidase inhibitors confirmed their therapeutic benefit in PD, but they had adverse reactions primarily involving cardiovascular stimulation as a result of peripheral monoamine oxidase limited the utility of this adverse reaction, primarily involving cardiovascular stimulation as a result of the periphery monoamine oxidase inhibition, which limited the utility of these drugs. And one of the major problems, as I've said, is that even if they had to take food compounds that had pressure effects, like theramine, then they would precipitate what we call a theramine, or they would precipitate what we call a hypertensive crisis. So it is very important for us to use selectivity, of course, to minimize toxicity. But why I say it's a good answer, yes, but you need to show that where is this toxicity originating from. So when you answer such a question, it's good to be a bit more specific so that you get the full mark. Synthesis of selegiline, it is a simple synthesis. It is synthesized by the alkylation of the minors. Remember methamphetamine. Remember this methamphetamine has a chiral center there, so you can get the dextro or the liver one. So you are alkylating the liver methamphetamine using 3-bromo, 1-propane, 3-bromo. So it's 1, 2, using 3-bromo. So it's 1, because we have always to start from where you have your functional group, which is a triple bond. So carbon 1, carbon 2, carbon 2, carbon 3. So it is 3-bromo, 1-propyne, showing, of course, it has a triple bond. And this is just an addition whereby the bromine, remember, always leaves a positive behind, and that positive will, the nitrogen, which has a lone pair of electrons, will attack the positive point and an addition reaction. So that is our selegiline. You can see, again, when you look at it, we still have structural similarity with dopamine. Moja kidogo, sijui kwa nini imeleta So you can see when you look at it again, we still have a structural similarity there with dopamine. So structural similarity with dopamine, whereby we have that is the RL group 1, 2, and we have a terminal tertiary amine. Of course, when you ever get that methyl group, this methyl group is usually important in blocking the metabolism. Very important in blocking metabolism by the monoamine oxidases, and therefore giving this compound, when it binds the monoamine oxidases, it is not readily metabolized by the monoamine oxidases. And of course, this group, as we realize when we look at the sympathomimetics, we realize it's not more that its importance is not more to give the compound lipid solubility. Of course, it will add the lipid solubility, but the biggest advantage of that group is to decrease the accessibility of the monoamine oxidase, and therefore giving that drug a longer period of activity. So definitely this compound, we are saying, you bind the receptor more firmly. It is an irreversible inhibitor of the monoamine oxidase B, completely destroying it and allowing, of course, for higher concentrations of dopamine, and hence relieving again the symptoms of Parkinson's disease. So pharmacologically active is again the R enantiomer, and the monoamine oxidase B is found in high concentrations in the brain, whereas type is restricted to the intestines and the liver, and is a reversible inhibitor of monoamine oxidase B by acting as a suicide substrate for the enzyme. Remember when you were doing the penicillins and you were doing the monoamine again, you were doing the what are we calling them? The beta-lactamase inhibitors, including the clavulanic acid and so on. And we did mention that you have suicide substrate. When we talk about suicide substrate, it's a substrate that it's a substrate that will be taken up. The enzyme will go for that substrate. But once it binds that substrate, it is completely bound. It is irreversible. It's suicide. It's like it has committed its own suicide by going for that substrate. So the enzyme, the monoamine oxidase B, will go for deselegiline total or irreversible, but the compound that will be formed will be totally stable. And since it is totally stable, then the enzyme will be totally held, not available to metabolize the dopamine. It is converted by monoamine oxidase B to an electrophilic species that combines irreversibly with flavin cofactor attached to the active site of the enzyme. So the monoamine oxidase, the substrate first changed to an electrophile, and then the electrophile, the substrate, the drug is first converted into an electrophile, and once it's converted to an electrophile, then it binds the enzyme permanently, resulting in its non-availability to destroy the dopamine. Selegiline is selective for B type of therapeutic concentration. Monoamine oxidase metabolizes telamine in the periphery and is not blocked by selegiline, avoiding a hypertensive crisis. So this is one of the things we are saying, very, very important, because you will be able to eat. Even as you take this drug, you can eat your foods comfortably. Telamine does not cross the blood-brain barrier, so it remains in the periphery. So even as you take it with your food, to remain in the periphery, it has pressor effects, and therefore, when you give selective monoamine oxidase B, you will preserve the activity of the monoamine oxidase A, and therefore, whatever requires to be metabolized in the periphery will be metabolized. An important function of the monoamine oxidase A, which remains intact with selegiline therapy, is that the enzyme provides protection from exogenous amines such as telamine, having potent cardiovascular stimulant activity. Mode of the breakdown. So if you look at it, as I said, you can see it has that. Its structure is similar to methamphetamine. You can see structure is similar to methamphetamine. So it's selegiline or N-propagil methamphetamine. This is the group. This group is what we call propagil. There, propagil. And of course, from that structure there now, that structure there is methamphetamine. So once it's metabolized, there is danger that it can be metabolized, or some of the byproducts can be amphetamine. And once you get amphetamine, you know amphetamine has CNS toxicity or CNS effects, and therefore it can have that kind of side effect. Its metabolism, you can have this methyl, you can have, you look at this methyl selagiline. So this is that group, oxidative end dealkylation, got catalyzed by mixed function. Don't require to exactly know the enzyme, but you can always say it's mixed function oxidases or cytochrome P450 enzymes to give us this methyl selagiline or N-propagil amphetamine. Then again, that can undergo further metabolism by, again, cytochrome P450 to give us L-amphetamine. Of course, when you look at amphetamine, this methyl group creates a chiral center there, and you can get dextroamphetamine and levoamphetamine. When we look at the stimulants, which would be, I think, the next, we will discover that, of course, the dextroamphetamine is more potent than the levoamphetamine. But the levoamphetamine is to have CNS stimulant activity, and therefore it is a psychostimulant, and that, of course, can be a toxic effect. And of course, also, this again can also be metabolized again by cytochrome P450 enzyme to give us again L-methamphetamine, again also a compound which has quite good, which is a CNS stimulant, and then of course again further metabolized to L-amphetamine. And this metabolism of these drugs to the psychostimulants is a disadvantage because of the toxicity. We have another drug we call osagiline. You can see again, as we have already looked at, you can see it still has that structure there. So you can see, but this one, you can see that is the phenyl ring. And that, so this one, the terminal nitrogen is separated from the phenyl ring with carbon atom, and like dopamine, where of course we have separation is two carbon atoms. So there's that slight difference, but it has still been found to have good activity. But now if you see, so the difference between that and that here is that, of course, this is a bicyclic. It has a heterocyclic ring, whereas the other one are just an aliphatic ring. Highly potent, selective, again, irreversible mitochondrial monoamine oxidase inhibitor. It inhibits steatodopamine metabolism. So it inhibits the steatodopamine metabolism, thereby providing relief from motor symptoms of PD. So you can see this is not really working in the brain, but it is selective. Highly potent, selective, reversible mitochondrial monoamine oxidase inhibitor, but within the striatomuscles, and therefore also inhibiting the metabolism of dopamine. You have high concentration of dopamine, and therefore bringing down providing relief from motor symptoms. It may be dosed once daily, and unlike selagiline, it is metabolized to non-amphetamine compounds, and therefore much lower toxicity. In a larger clinical trial, osagiline has proved effective, safe, and well tolerated in early PD as monotherapy. So it has a slightly different mode of action. It is working at the muscles itself. It's providing the muscles with higher levels of dopamine, and therefore relieving the symptoms of PD or Parkinsonism. So you can see the advantage of that structure, and we are seeing that structure because of that difference, whereby this diamethylnitrogen is separated from that phenyl ring with one carbon. There is no way, even if you try to metabolize it, there is no way it can give us. There is no way it can give us amphetamine or methamphetamine at any one time. So rosagiline undergoes extensive hepatic metabolism and almost complete bowel transformation in the liver, primarily by, again, cytochrome P450 or mixed function oxidases to form the 1R aminoidane, which is a major metabolite. Which is to form the 1R aminoidane, and this is that compound. So, but we will look at it. Can also form 3-hydroxy N-propagyl 1-aminoidane and 3-hydroxy aminoidane. I believe I have the metabolic process or the scheme. So you look. This is for serragiline. Oh, the rosagiline is here also. So that is our rosagiline. And if you look at the metabolism catalyzed by cytochrome P450, it is just oxidative end dealkylation. We are losing the Pagyl group. This is a group, we are losing that group, and it becomes aminoidane. So you're left. That's the main metabolic, that's the main metabolite, but you can also have hydroxylation. You can also have hydroxylation. You can also have hydroxylation. I don't know whether I gave, where you can get the 3-hydroxy N-propagyl 1-aminoidane, which means 3-hydroxy means, see where you can start position 1, 2, 3 here. You can see this is the 3-hydroxy, because that was not there before, was it? No. Yes, you can see. So position 1, position 2, position 3. So that is the product we are calling. So you can have the 3-hydroxy N-propagyl 1-aminoidane. So that N-3-hydroxy N-propagyl 1-amino. This is a compound we are calling aminoidane, that one. So we are only saying it can also, the main metabolic process is oxidative dealkylation of this group there, but it can also undergo, it can fail to go the oxidative dealkylation, and it can undergo hydroxylation. So it can undergo hydroxylation, or it can undergo, so it can undergo hydroxylation the way it is to give us the 3-hydroxy N-propagyl 1-aminoidane, or it can undergo the N-dealkylation. Once it undergoes the N-dealkylation, then it undergoes hydroxylation to give us the 3-hydroxy aminoidane without the propagyl. I hope you are together. So you can have oxidative dealkylation, so you lose that group, and the compound undergoes oxidation. And once it undergoes oxidation, it will give us a 3-hydroxy aminoidane. You can retain that group, and that undergoes oxidation. When that happens, then of course you get the 3-hydroxy N-propagyl 1-aminoidane. Or you can lose the whole of that group and not have also oxidation, and that is where it will give us the aminoidane. So those are the main routes of metabolism. I hope you have understood that you can get that. That's just one, which is a major one, but you can get this compound undergoing loss, oxidative end dealkylation and oxidation, or you can have this compound undergoing oxidation to give you the products that I've already discussed. So this compound, the biggest advantage is that, as we have said, it will not be metabolized into, it will not give us the amphetamines, and this is just further emphasizing the same. That is selegiline, this methyl selegiline, and of course the selegiline can go to amphetamine, and that this can go also to L-amphetamine. That's where we got to. But of course we are saying also this ring can undergo oxidative hydroxylation to give us L-parahydroxy N-methylamphetamine, but the other earlier one we came up to there. So this is just to a lower extent. And then you can have this methyl selegiline giving you L-amphetamine, as we had said, and also can give you L-parahydroxyamphetamine, again, para they forgot to put a para-hydroxy group there. Then we are looking at rosagiline, and we have said you can go to aminoindane and N-acetylaminoindane, so that can also be acetylated. This is supposed to be NH2. This acetylated will be NH, double bond O CH3, so you can write it properly. So there can be acetylation of that amino group, or it can be rosagiline, where, these are different drugs. So you can have rosagiline going to aminoindane, going to the N-acetyl aminoindane, but we also learned that you can have rosagiline also being cleaved, not cleaved, and undergoing 3-hydroxylation, being cleaved in addition to the acetylation. So we have said that rosagiline also undergoes extensive metabolism, complete extensive metabolism, so it will be excreted as mainly the metabolite. And we have compared the metabolism of rosagiline and the metabolism of selagiline. And we are saying selagiline can result more CNS toxicity as compared to rosagiline, and we have explained why. The other one, so we are done with monoamine oxidase inhibitors. The other enzyme inhibitors are the COMT. Because of the existence of the hydroxyl groups within dopamine, because of the existence of the hydroxyl groups within dopamine can be metabolized into its catechol-methyl, into its methylated or methoxy derivative. The same case that happens to L-dopa, because it also has hydroxyl group, can be metabolized to the methoxy derivatives. And therefore, if you block these enzymes, you will give these drugs a longer half-life, or a longer transference of COMT activity in both periphery and the CNS enhances the bioavailability of L-dopa. Examples include tocapone, an inhibitor of COM2, COMT in both the periphery and the CNS, and it has a much higher activity. CNS activity than periphery. It has higher CNS activity than peripheral activity. You also have entacapone. It is less potent and less readily distributed to the CNS. The nitrocatechol structural features. So when we look at them again, you see they have a nitrocatechol. Again, nitrocatechol meaning the catechol, the phenyl ring has a nitro substituent. So you can see it is two, the phenyl, that's the catechol, and then an extra nitro group. So we are talking about the nitrocatechol. So that is in tocapone. And even if you look at tocapone and entacapone also has a nitrocatechol. So it's good to understand when we talk about the nitrocatechols, that's what we were saying, that the nitrocatechol structural feature of both drug confers affinity for the active site of COMT. So that group is just to endear this molecule or this drug to the COMT receptor. There's action. So we have those two groups. The one which has the acetophenone. I think it's one which has the acetophenone. This is the one which has the acetophenone. It really doesn't have an acetophenone because it doesn't have a ketone group there. But we are saying this group here. So perhaps you can put it as that group there. But that group there is allowing this molecule to be able to have antagonistic activity. So the catechol, remember this catechol group also is found in dopamine. So when you put the nitro group, then it gives it better affinity for the COMT receptor. But it should have affinity an antagonist activity. So it has affinity to bind the receptor. And then this other group that has been added on, I will consider both of them, because even this one has an acetal, but it's not an acetylphenyl group, because you can see if it was to be an acetylphenyl group, it will be directly attached to the phenyl, and that's not what has happened. But it still has an acetyl group. I think what we need to consider is that this other added group in both drugs, of course, in tocapone, which has much more, you can see that acetyl group is directly attached to the nitrocatechol ring. So that is giving it even better antagonistic activity, I believe, compared to the entacapone, which does not that. So we are saying the acetylphenol moiety, which we have seen is mainly in tocapone, produces antagonistic activity. Tocapone has been characterized as a tight, so it binds a receptor, a tight fitting molecule, as a tight binding competitive inhibitor of COMT. Of course, once it binds tightly, once it binds firmly, it remains a long time, and it's an antagonist. Of course, it has very good activity. And for all drugs that have antagonistic activity, you find that they have extra groups. They have higher substitution, and that higher substitution allows them even to bind other areas within the receptor, but they bind and the compound does not have or does not trigger any pharmacological activity, and it prevents, because it's binding for a long enough time, it prevents the agonist from binding the receptor. The entacapone has the E stereochemistry about the double bond. The major metabolite of entacapone is its Z isomer. The therapeutic activity results from increased bioavailability of L-DOPA to site of action, and of course also reduction in formation of the potentially toxic metabolite. So we are saying, like, if you are giving, because we said you normally don't give L-DOPA alone. You give L-DOPA. Oh yeah, if you are giving L-DOPA, you don't of course give dopamine. When you're giving L-DOPA, you are saying that L-DOPA, because it is metabolized by catechol methyltransferase, by methylation of the 3-hydroxyl group, then it will last a little bit longer. It will be more available. Of course, when it's more available, then it's more available both in the periphery and also in the brain, then it will be converted to dopamine. Once it's converted to dopamine, then of course it will have a relief of the PD symptoms. Reduction, of course, also there is also a metabolite. When L-DOPA is metabolized, but catechol methyltransferase, it gives us the metabolite we are calling the 3-O-methyl L-DOPA. This metabolite has also been found to have high toxicity. So also it has this drug, it helps or is found to bring about its action in two ways. It reduces the formation of the potentially toxic metabolite 3-O-methyl L-DOPA, and also in itself it increases the concentration of L-DOPA, and therefore L-DOPA is more available to be metabolized, to undergo oxidative decarboxylation by L-DOPA decarboxylase. You have blocked the COMT, you have blocked the ME, you have given in combination, you have blocked also. Then you can also block, of course, the monoamine oxidases, and therefore you have more. The L-DOPA is highly available to be converted into dopamine, and of course the dopamine now, to bring in a balance, there will be a balance between the dopamine and of course the acetylcholine, helping us to manage the symptoms of Parkinson's disease. So you have these two drugs, there's tocapone, and you can, as we have said, there is similarity in that structure. There, similarity in this structure. So this time, the similarity between dopamine and these compounds is not in, it is in the catechol, but you can see that we do not really have an ethylamine structure, but there is a catechol which is similar, and that catechol allows, because remember this is catechol O methyl transferase. So indeed, this drug can metabolize anything which has a catechol, which is a catechol. So therefore, that's why when you look at the structure, we are not concentrating in the ethylamine, we are looking at the catechol, because the enzyme is metabolizing the hydroxyl groups within the catechol. When we looked at the monoamine oxidases, there was some similarity because the enzymes were metabolizing the monoamine oxidizer. So there was structural similarity with these other areas. So that is of importance to note, that depending on the mode of action of the metabolizing drug, then you will be able to develop an appropriate antagonist. So that is the talk upon and that one. And we are saying they will decrease the metabolism. You can have L-DOPA when R is a carboxylic group. You can have dopamine when R is a hydrogen. And remember, both of them are metabolized by catechol methyltransferase, and you have